I know, pick me. Calculating pH, 0.1 mole per liter. Here's an acid. Yeah, it's called acetic acid, by the way, or ethanoic acid. Oh, just go negative, log that concentration. pH is 1. Oh, I know, 1.00 because there's 2 significant digits. No, wrong. That's wrong. What do you mean it's wrong? And what's the matter? This is what's the matter. That's a weak acid, and weak acids don't dissociate 100% to make hydronium in solution, or to react with water 100% to make hydronium in solution. What do? Look, when you're given an acid-base chart, or you might not be given a chart, but you're given information that gives a K value for a chemical that is not going to be very large. In our acid-base charts that we have in the province of Alberta, we've got 6 strong acids in the top, and the K values for strong acids are so huge we don't even care what they are because they dissociate 100%, so we know what the concentration of the products are given a concentration of reactants in a dissociation. But the weak acids, which are all listed down here, man, those weak acids all have K values that we're going to use as equilibria types of calculations to be able to determine their pHs. Here's the deal. Acetic acid or ethanoic acid, which is right here, has a K value which is given, and we're going to utilize that. All of these names here correspond to these acids here. When you lose a proton from every one of these acids, it forms these chemicals called their conjugate bases here. These charts are generally arranged where the strongest acids are on the top left corner, and they descend in terms of, well, these are all strong acids and they're all represented by hydronium right here. And everything underneath that is a weak acid. There's a strong base, hydroxide ion, and everything above that is a weak base, and it gets weaker as you go up. Strong acids gets weaker as you go down. Kind of arranged like the redox charts are in terms of the strength of oxidizing and reducing agents. Here's the deal. How do we take that chemical and find the pH? Here's what we remember. That CH3COOH plus water is going to give us, now look, you always take, whatever it's an acid or a base, in this unit of study, acids and bases, always just take the chemical and add it to water. And then transfer a proton. For a proton from the strongest acid here to the strongest base, which is the water, to get hydronium ion. That's hydronium ion, that's a 3. And what's the conjugate base ion here? It's called acetate ion, CH3COO negative. Guess what? You got an initial concentration here, 0.10 moles per liter, but you ain't got nothing here initially and nothing here initially. And then there's a change and then equilibrium. This is an equilibrium problem. And so this is going to lose X of itself to make X here and X here to be able to get, at equilibrium, 1.0 minus X, X, and X. You know what? When we set up the equilibrium expression for this, which is going to be this times this, the K, oh what K? It's an acid dissociation, so it's called the Ka. And that equals the concentration of the hydronium times the concentrate of the acetate ion, right? All divided by the concentration of the CH3COOH here. Now, when we plug all the numbers in, 1.8 times 10 to the negative 5. Where'd you get that from? I got it from the information provided on the chart here, which says that the Ka is 1.8 times 10 to the negative 5. If you weren't given a chart, the question will always have in it, here's the concentration of that, find the pH, the Ka equals, and it'll tell you the K value. So, what's these two? X squared, divided by the concentration here, which is 0.10 minus X. Now, I'm going to tell you that generally, how do we know that if X is disregardable or not? Well, remember, we take the initial concentration of the chemical, 0.1, divided by the K value. If you get a number that's greater than or equal to 1,000, you can disregard that value for X. In our province, we have questions that are given on our major diploma exams at the end of the course, where students write an exam that's worth 50% of their mark overall in the course. Nobody's interested in giving them an X value that they have to keep in here when calculating a pH. And so generally, you know what you're going to get, and especially on like IB exams and AP exams, they don't want you to necessarily do all the math and have to worry about math. They want you to worry about chemistry. So they're going to give you questions where you can just disregard X. And so that X, which is going to be a very, very small number anyway, taken away from 0.1, doesn't even matter. When you calculate here, for x is going to equal the square root of, are you with me? 1.8 times 10 to the negative 6. Because that times that is 10 to the negative 6. Take the square root of that, that's x. But what is x? X is the hydronium ion concentration. It's that. And so now all you have to do is take the negative log of that, right? So the negative log of that number there, and you're going to get 2.87, and that's the pH. Yep, the pH of that, if it was a strong acid, would have been 1.00. But it's really 2.87 because it's a weak acid. Now, so again, 2 significant digits, and there was 2 significant digits in the Ka value, so that's why I kept 2 numbers after the decimal in that pH. This is how you calculate the pH of a weak substance. And what's it always going to degrade into, really, so you can do the question a little bit quicker instead of having a whole icebox to do? It's always going to be Ka equals x squared over the concentration. So really just take the concentration times the K value and take the square root of that, and that's the hydronium ion concentration. It'll always break down that simply into that.